So, chapter 2 or chapter 24, you can say. The title of this chapter, Gauss law. Okay. What did we study in chapter 23? That there are two kinds of charges, positive and negative, and there is electric field. There is electric field between these two charges. Okay, and we study the Coulomb's law and electric field, how to find out the electric field, and F is equal to K, Q1, Q2, R square. Coulomb's law, F is equal to Q E. Okay. So we were dealing with the static charges. Okay, there is two charges like this, and there is electric field between these two charges. Okay, static charge. Still we are studying the static charge. In Gauss's law, this law actually based upon the Gauss, one of the scientists, and he studied the charged particle inside the sphere and how to find out the flux. So we start from the flux. So what is flux? If you have this paper, an electric field is passing through. Okay, electric field is passing through the area of the any kind of surface. That is called flux, and it's denoted by phi. Okay, electric field is area A. Okay, so electric field lines per unit area perpendicular to the field. So phi is equal to this is a vector quantity or scalar? Scalar quantity. And this we also call dot product. Okay, dot product. And the magnitude we like EA cosine theta. Okay. So if you have a surface, any surface like this, okay, this is an electric line. And this is the area, any area, and the normal on the area, normal to the area. And you know the normal? The concept of normal is this line, if you draw it, this is normal. Okay. So, if you see in this case, the electric field is there, this is the area from where the electric field lines are passing through, okay, in certain area. And theta is the angle between E and A. E and A. Electric field and area. So, in this case, what is the value of theta in this case?
0. There is a
Normal and electric field. Normal to the area, okay, and electric field. If this is a normal, electric field is also in this direction. Okay, so theta is 0. So if theta is 0, cosine theta is equal to 1. So it means in this case you have maximum flux. Maximum flux. Okay, so maximum electric field lines are passing through. Okay. Now, if you have theta 90 degrees, it means this is your N and this is your electric field. So this N beside A, yeah. What is the function of the area? So here, in case of 90, what you have, cosine 90 degree is equal to what? Zero. So if surface like this, then you have phi is equal to 0. No flux. Okay. So this, there can be any arbitrary angle between the area and electric field. It can be 0, it can be 90, it can be 180, or you can make it 45, whatever it is. Okay? So, but the maximum flux you get when theta is equal to 0. The angle between the area and electric field, 0. Okay? Okay, so if you have any surface, and first thing, this is scalar quantity, it's a dot product, okay? And what is the difference between the dot product and cross product? Cross product, you know?
Yes.
Yeah, so it gives a vector like this. Okay, in case of scalar, like W is equal to FD, this is dot product. Yeah, and this is scalar quantity. This is scalar quantity. This is vector quantity in case of cross product. Okay. So, if you have any surface, and let's suppose this is surface, and the electric field is not uniform. Electric field is not uniform, and we are supposed to find out the flux. So what we do? We divide this surface into small patches. Okay, and the area of the each patch we can say is delta A. Delta A, okay, small area, now it's not a big surface. And we assume that the flux or the electric field, actually not flux, electric field here, we assume that's uniform. It's not uniform for whole surface, okay? But we assume that it's uniform for this one patch, okay? So, in this case, area here is delta A, delta A, delta A1, A2, 1, 2, 3, 4, 5, 6, 7, whatever it is. Okay. So in this case, and we want to find out the flux through whole surface, and the area of one patch is delta A. So what we do here, you can write E summation to sum up all the areas, the electric field through this area, this area, and then sum up, so that we can get total flux here. Okay. Now, so equation will be now if this area is delta A, if this area is getting very small, approaching to 0, we say So then this delta A will replace the D differential. Okay, it's very small area now. Okay, so now in this case, to find out the total flux, what we do, we use the integration. Integration. So flux through this small area, say E dk. Flux through this small area. Okay, it's very small now. dA. And now to find out the total flux, you just integrate here. Phi is equal to dV. Okay, so in this case, you can find the flux. If the electric field is not uniform, what you do, you divide it into small parts and then see individual flux and then sum up all this. Okay, so this is the basic concept of flux. Now there is one example actually how to find out the flux in your book. Simple. Do you have book, by the way? No book? Nobody? No book? Okay, so there is a problem, and in this problem we are supposed to, I don't remember now, and this is not working properly. I cannot show you. So we are supposed to find out flux, and but in that problem electric field is not given. Electric field is not given. So what they have given the charge value, and they have given the R value. R mean, remember R? Yes, so first we need to find out electric field. Okay, the charge is given. Charge is 1 10 to minus 6 coulomb, and R is 1 meter. Okay, so which equation we can apply here? K Q over R square. Remember the last chapter. Okay, so K is a constant which is 8.9 into 10 to 9, and this one is 1 into 10 to minus 6, and 1 square. So what value is coming here? 8.99 10 to 3 Newton per coulomb. Okay, the E value. Okay, this is E value, electric field. But to find out the flux, you need EA. Okay, so R value is given. This is a question about the sphere, something like this. Okay, the R value is given. Charge is given, what is charge inside, and R is also given. And we have to find out electric field, which we have done already, and we also need to find out the area. So area of the sphere is equal to 4 pi r square. Okay. So if you substitute the value here of R, so what you get is 12.6 meter square. Okay, so now the question is very simple. You know this value, 8.993, and multiply 12.6, and that would give you the flux, which is 1.1375 Newton. Okay, Newton. Now, let's suppose you have any sphere, okay, like a football, and you have a charge, and you want to find out the flux. Okay. So, this charge, it means there will be electric field, okay. So, the electric field going out, going out, going out, going out, going out, going out. It's like a football, okay? And all the electric field is directed outward. We assume a small patch here, and this electric field is passing through, and the area is dA. Okay? Now, area and electric field, the angle between them is 0. From all the sides, if you take a football, from all the sides, the electric field, if you divide into small patches, the electric field and the normal to the area, they will be having 0 degrees between. Okay? Now, if you remember the formula, that phi is equal to this one, okay? So, sine theta and theta is 0, so it's obvious that EDA. Okay? EDA. Now, if you take out the electric field here, okay, so what it shows, this portion. What it shows?
The duration of dA.
Yes. Isn't it area of the sphere? Area of the sphere. So, the same thing come again. The area of the sphere. You go to your high school books of mathematics. The area of the sphere, not the circle. The area of the sphere is 4 pi r square. Okay? In the last problem, the area of the sphere is 4 pi r square. So the integral, so this is the area of the whole sphere, not the patch. Area of whole sphere. So it means you can write 4 pi r square. Okay? E. Okay? Is it clear? Now E, electric field is equal to what? Last chapter.
K Q over R square.
Q 1 over K, value of K is 1 over 4 pi epsilon naught Q over R square. This is like this.
Yes.
Okay? So we substitute this value here. 1 over 4 pi epsilon naught and Q over R square, and you have 4 pi R square. So this thing will become cancel here and this thing will be cancelled here. So what we get? Q over epsilon. So flux for a sphere, when the charge is enclosed in the sphere, so this is the value of the flux. So this is actually, this is called Gauss's law. Gauss's law. Okay? So when there is sphere and the charge is enclosed, okay, charge is enclosed, so the flux is equal to charge enclosed by 1 over permittivity. And permittivity is a constant depending on the medium. Okay? So this is the case to find out the flux from a sphere, and this is the Gauss's law. Okay? Now let's see some other possibilities. Let's suppose you have many surfaces like this, another surface like this, another surface like this. Okay. So we call it flux various surfaces. Okay. So flux through various surfaces and charge is inside. Okay. So it means the electric field lines pass through all the surfaces. Is it? There is one football, inside of it there is another football, inside of it is another football, and there is one charge inside of that. So the electric field lines passing through all the footballs. Okay? So in this case, this is surface 1, this is surface 2, this is surface 3. So flux surface 1 is equal to flux surface 2 is equal to flux surface 3 equal to Q in over epsilon. Okay, sometime in the exam they give this kind of things. Okay, they give the options. So what will be the total flux from here, from this kind of surface? You can have 4, 5, 6, 7, 8. How many surfaces? After that, another possibility, if there is a point charge outside of surface, any surface outside of closed. One thing I didn't mention actually. We are discussing here closed surfaces. Sphere is a closed surface. So Gauss's law is applicable to the closed surfaces. Charge is enclosed in the surface. So these are also closed surfaces. Okay? So these all things, what we apply here is applied to the closed surfaces, where the Gauss's law is applicable. Now point charge outside of surface or closed surface, if there is any surface and the charge is here, condition is for the, in this chapter, to find out the Gauss's law. How can you apply the Gauss's law? The surface should be closed. We always assume the closed surface. If the charge is outside, it means There is no charge inside. No charge inside, okay? So this equation, if there is no charge, this is the actual equation, okay? If there is no charge, Qn is equal to 0. Okay, Qn is equal to 0. So phi is equal to 0. Okay? So phi is equal to 0. This is one of the possibilities. Now, other case, flux through different surfaces. Okay? So flux through different surfaces. Suppose this is one surface, closed surface. Okay? There is a charge inside, we call it Q. Okay? And this is a charge, Q1. There is another surface, it has two charges. Q2, Q3. Okay? Another surface, there is no charge inside but outside. Okay? And we want to find out the total flux here. So how will you find out the flux here? Total flux. Total flux. How will you find out? We know that this is the formula. Okay. So if you have many charges, you can apply the summation. Okay. Now you have to look surface 1. Okay, surface 1 is having Q1 epsilon naught. Surface 2 is, you can say, is 1 and is 2 and is 3. So surface 2 is having Q2 plus Q3 epsilon naught. And how about this one?
0.
So it means flux through one surface is this one, and flux through the other surface is this one, and flux through third system is this one. So this summation actually we apply here. Okay? The two charges. There can be 3 charges, 4 charges. If the charges are inside, they will satisfy. If the charges are outside, they will not satisfy to apply. Okay? So flux, we can find out if the charge is flux, you can do zero flux. Zero flux if there is no charge inside. So, but in this chapter, what we are supposed to assume that we are dealing with a closed surface, and the Gauss's law is only applicable when the charge is inside the surface. Okay, enclosed inside the surface. And whole this chapter actually is based on Gauss's law. That is why the title is Gauss's law. So we apply this thing